Section 2.2, basic properties of vector spaces. So we consider this again in the abstract setting where we have V vector space over field F. And again, we consider theorems and proofs. First theorem in this section, this is about the zero vector. So this is basically playing with the definitions, trying to figure out what is defined and trying not to confuse what you already know from undergraduate studies with what we defined in the definition of vector spaces. So this theorem says that for a scalar A and a vector V, what we have is AV equals to the zero vector if and only if either A is zero, scalar in the field F, or V is the zero vector in the vector space V. So we have a lot of these if and only if statements. And this means we have to show equivalency. We have to show implication in two directions. And usually we do this in two steps. So first we go in this direction from right to left. Case 1, A equals to 0 in the field F. Again, this might look trivial. What do we need? We multiply by 0 and we get 0. What is important to remember is that the definition of the zero scalar, it's not about the scalar multiplication. So F is a field, it has its own multiplication and addition, more importantly right now. So the definition of the zero scalar is actually that for all entry or element B of this field F, if you add 0 and B, it doesn't change this. But this is for scalars. And this is about addition. And actually we want to talk about now multiplication and scalar multiplication of a scalar and a vector instead of addition of scalars. So this is the neat thing that we go from one operation to a completely different operation with the zero. Now, in particular, from this definition, we can set a B equal to the 0, and what we get is that 0 plus 0 equals 0. So we want to go backward from right to left, so we want to examine this left-hand side equation. A times V. What is A times V? What we have is that A is now 0, so we have 0 times V. And then what we have from this previous identity is that this is 0 plus 0 times V. And then we have the distributive property from the definition that says that this is 0V plus 0V. Then we compare in this equation these two parts. And let me write this down again. So we have 0V plus 0V equals 0V. This is all in V, which is a abelian group with additive inverse. the additive inverse is usually denoted by minus. So we add this additive inverse to both sides. Well, usually we write minus, but this is supposed to be really defined as plus the additive inverse. Yeah. So plus minus is really minus, but we only have the plus defined in the vector space, and usually the minus is defined as plus minus. And then, of course, we have cancellations. So because of the additive inverse, we get 0 on the right-hand side, the 0 vector, and the left-hand side we get 0v. So this shows that AV, which is 0v, is the 0 vector. And this is what we had to show to go from right to left, that AV is the 0 vector. So this was case 1, when A is 0. The other case is if V is the 0 vector. It's similar proof. So we have now the definition of the 0 vector in V, vector space, is that for all vector W, if you add 0 vector to this W, it doesn't change the W vector. And then again, as a special case, we set W equal to 0. So what we get is that 0 plus 0 vector is the 0 vector. And then we write A times V vector, which is now A times the 0 vector. Substitute the 0 vector with 0 plus 0. Distribute. We have the distributive property with respect to the scalar multiplication with respect to the vector addition. So we get A0 plus A0. Again, we compare these parts of the equation. It says that A0 plus A0 vector is the A0 vector. Again, we use additive inverse. Since this is in the vector space V, it has additive inverse minus A0. And what we get is that A0 plus A0 minus A0 equals A0 minus A0. And after cancellation, we get that A0 equals to the 0 vector. And since this was AV originally, we proved that AV is 0, which is the left-hand side of this if and only if statement. So with this, we finished the two cases of one direction. Then we continue with the other direction from left to right, which is assuming that AV is the 0 vector. Again, we have split this into two cases. If A is 0, then we are done, since this is one part of the right-hand side of this if and only if statement. Case 2, if A is not equal to 0, A is a scalar. The scalar field has its own multiplication and addition, and if A is not 0, then it has its multiplicative inverse. It's denoted by A to the negative 1. Yeah, I didn't discuss this in detail, but again, just think about the field as a real number set. So real numbers, if a real number is not 0, then it has its reciprocal. So the multiplicative inverse for real numbers is really just the reciprocal. Real numbers has their own addition and multiplication. And the property of this multiplicative inverse is A inverse is 1, where 1 is the this unit element in the field, or it's the multiplicative identity. Then we had this before, that with this we have that when you multiply this with a vector 1 times v, this scalar 1 times v, it's the same as v. And then now we substitute 1 with this A inverse. Then we use this associative property that we can redraw these parentheses and write, and also actually there is a commutative property, maybe that's how I could have written down also that A inverse A is 1. So if I write it as A inverse AV, then AV is assumed to be 0. So we have A inverse the 0 vector, and we already know from case 2 of the first part of the proof that if you multiply with a 0 vector, a scalar, multiply a 0 vector, you get the 0 vector. So we get from here that if A is 0, we are done, and if it's not 0, then V must be 0. Which completes the proof. Lemma 2.2.2 is about the additive inverse of V. It's a very small lemma. It says that for all vector V, minus 1 times V is minus V, which is the additive inverse of V. Again, the importance of this lemma is that it goes from minus 1, which is the additive inverse of 1 in F. It combines this with scalar multiplication, minus 1 scalar with the V, and it turns into additive inverse in the vector space V. So this is the importance of this lemma, that it combines the additive inverse of F now with the additive inverse of V vectors. The proof, well, we have to show that it's the additive inverse of V that we get. That means that we have to show that when you add together minus 1 times V with V, you get the 0 vector. We know about minus 1 in F, that minus 1 plus 1 is 0. So when we write minus 1V plus V, we already know from the basic property that V is the same as 1 times V. And then we use the distributive property of scalar multiplication backward now, that we factor out V from this sum. And because we already know that in the scalar field we have minus 1 plus 1 is the 0 scalar, and because of the previous theorem, we know that if you have the 0 scalar multiplying a vector V, we get the 0 vector. The proof is complete.